Okay, hi everybody. Welcome to part 2 of 5.6 video notes. Okay, we're going to recap what we did in class with quickly going through number 8. So we're solving, remember, which is not simplifying to a single fraction. Our goal when we're solving is actually to get rid of the fractions altogether. This one's kind of nice because I only have one fraction, so I only have one denominator. So all I have to do is multiply everything by this one denominator. So on the right-hand side, I'm multiplying by 2x minus 7. On the left-hand side, I'm multiplying by 2x minus 7. But here's my caution with a problem like this. So you see the 3x and the 5. You can go about it one of two ways. You could just distribute it to the 3x, then distribute that whole thing to the 5, or you can think of it as times that binomial as a group, which is what I do just to make it a little streamlined. Okay, so I'm going to multiply everything by 2x minus 7. So I'm going to do 2x minus 7 times 3x plus 5. Then when I multiply 2x minus 7 times the second one, that's intentionally going away. And I just have 8 because the numerator and denominator cancel. That was the goal. And then on the right-hand side, 6x plus 1 times 2x minus 7. Okay, so remember that that's always going to happen in the first step. If you multiply by the common denominator, from original problem to that next step, all of your fractions should be gone. Now it's just a matter of doing a bunch of algebra. So we're going to be distributing here. So 6x squared, 2x times 5 is 10x. I'm going to do this all in one step. So 10x minus 21x is negative 11x. Just get my notes out so I don't make any silly mistakes. Okay. And then negative 7 times 5. Then same thing on the right-hand side. I've got two binomials, so I'm going to distribute. 12x squared. 6x times negative 7 is negative 42x. Is that right? And then 1 times 2x. So negative 42x plus 2x. Just making sure. 1 times negative 7. Good? Okay, fractions are gone. I've distributed. Let's get everything on one side. So I've got 6x squared. I'm going to subtract that over. I'm going to add the 11x over. And then this right here, negative 35 plus 8 is negative 27. So I'm going to add 27 over. So plus 27 plus 27. And then we'll see where we ended up. So 6x squared. Negative 40 plus 11 is negative 29x. Negative 7 plus 27 is plus 20. You guys with me? It's pretty boring. Okay, now what? Factor if we can, or you can jump right to quadratic formula. I don't care. I like to see if it factors just for fun. Can you think of something? Let's see, 6 times 20 is 120 and negative 29. So you do have to do a little bit of checking and guessing here. Things that multiply to 120, 12 and 10. That doesn't combine to 29. What else? 5 and 24. Negative 24, negative 5. There we go. I really did just stumble upon that. Okay. All right, so that's going to help me build my area model. I'm taking the time to go through this factoring just because we could all use a little factoring practice. Okay, so that's negative 24x, negative 5x. So 6x needs to go down here. 1x needs to go there. And then we can fill in the rest of our box. Okay, so we've got our factor form here. It's 6x minus 5 times x minus 4. Okay, so I'm kind of going a little quickly through that because this is not new for you. So we get our two solutions. This x minus 4 factor, if I set that equal to 0, you just get 4. If you set 6x minus 5 equal to 0, you get positive 5 over 6. Before I circle that and move on, we just need to look at the restrictions and make sure neither of those are a restriction to our denominator. Are either of these a restriction in this original problem? No. So the only restriction we see here would be when x is 7 over 2. So these are both fine. Okay, so we reviewed the process. You pick the common denominator. This one was just 1. Multiply everything, eliminate fractions, and then lots of algebra. Now we're going to apply our knowledge to word problems. Okay? Turn the page and then skip that page. I don't like this problem at all. So completely skip problem page 23. We're going to look at example 10. So we're going to be looking more at the relationship between distance, rate, and time and building on our understanding of that. Except in this case, all of our trips, like everything is always affected by some other speed. So these are always going to be boats in a river that are affected by current, or airplanes that are affected by wind, headwind and tailwind and stuff like that. So these are going to be a little bit different. So let's read the problem. The current in a river is 3 miles an hour. Speedboat went downstream 6 miles and then returned 6 miles. So it went down and back in 15 minutes, which, by the way, since we were given rate in miles per hour, we need to count time in hours. So right away, we should be thinking, instead of in minutes, we should be thinking in hours. So we're going to fill in 1/4 of an hour instead of 15 minutes. What was the average speed of the sailboat R relative to still water? So I'm just going to draw a little picture. Here's a river. The current kind of looks like bacon. There's a river. The current is flowing downstream. If the current is 3 miles an hour and a boat is set to go, it's a speedboat, so you set the speed. Whatever speed it's set to, it's actually going to be going 3 miles an hour faster than that, right? It's going to like boost it, that current. And then on the way back upstream, it's going to be facing a 3 mile an hour current. So it's going to slow, like if the boat is set to go at 30 miles an hour, 3 miles an hour are going to be taken off of that, what's actually happening. So what this is asking for, the average speed of the sailboat, it's a speedboat. Relative to still water means what is the speed set to? We know how fast it's going to be going because once we figure out the current, but we want to know what is it set to. Okay, so we're going to set this up the same way we did on our other word problems. Downstream and upstream, we've got two relationships between distance, rate, and time. Do we know the distance downstream? 6 miles an hour. Do we know the rate of the boat relative to still water downstream? No, we don't, but whatever that rate is, as it's affected by the current, we're going to add 3 to it. Because if it's set to R miles an hour, it's actually going to go downstream, R plus 3 miles an hour. Do I know the time downstream? No, I don't. I'm going to put T1 because now we already know those are going to be 2 different T's. All right. Do I know the distance upstream, Jordan? speedboat went downstream 6 miles and then returned.
Oh, downstream.
It returned 6 miles.
Oh, so yeah.
Yeah, so 6 miles. 6 down, 6 up. The rate coming back up, if it was R+3 going downstream, and then it's facing a 3 mile an hour current going upstream, is going to be R-3 on the way back. Does that make sense? Okay, and then T2. Now, are those two times going to be the same? It's going to be a faster trip downstream, right? Longer upstream. The reason this problem is different than the ones we've seen like this is we were using that relationship that the average rate equals total distance over total time, right? Total time. I have total distance and I have total time. That can't be applied to this because I want the rate relative to still water. So I can't, like, this would just give us the average rate that the boat traveled. We want the average rate that it was set to travel after or before it was affected by still water. So this. The good thing is I know the total time. How's that going to help me? I know T1 plus T2 equals 1/4 of an hour. Can I get T1 and T2 from these equations? Can I solve for T1 here? Yeah. Yes, question mark? Yes. So if I know the total time is 1/4 of an hour, and I have a relationship with T1 and T2 in it, then we can just do this. Divide both sides of my first equation by R+3, and we get 6 over R+3. T2 is 6 over R-3. So just from our distance, rate, and time equations, solve for T1 and T2, and then the fact that we know their total time is 1/4 of an hour, we can just plug those fractions into T1 and T2. So that'll be 6 over R+3 plus 6 over R-3 equals 1/4 per 1/4 of an hour. So now we've taken the information in the word problem, and now we just have a nice, simple, rational equation that we now have a strategy to solve. So to solve this, I don't want to simplify it. I want to actually solve for R, essentially meaning get rid of all the fractions. So what do I need to multiply by to eliminate all 3 of these fractions? That's right, the common denominator. What's the common denominator? All 3. Yeah, the product of all 3. So I need to multiply each side by 4, R+3, R-3. 4, R+3, R-3. Okay, so in this single step, we should eliminate all fractions, right? So when I multiply this by the first fraction, work carefully here. R+3 in my denominator is going to cancel with R+3 in my numerator, leaving just the 4 and the R-3. So it's going to be 6 times 4, which is 24, times R-3. When I multiply it by the second one, the R-3s are going to cancel. And it's just leaving 6 times 4 times R+3. So 24 R+3. And then on the right side, the 4's cancel, and it's just R+3, R-3. Okay, the fractions are gone. Now we just, oh, thanks. Okay, now let's distribute. 24R minus 24 times 3, which is 72, plus 24r plus 24 times 3. So this is nice because when this happens in this type of problem, you're always going to see the negative and positive of that number cancel out. And then you're just left with 24r plus 24r. So 48r on the left. On the right, we need to multiply r plus 3 times r minus 3, which is a difference of squares. So that's going to be r squared minus 3r plus 3r. So the middle terms always cancel out in a difference of squares. So it ends up just being r squared minus 9. Okay. Now what? That's right. Put everything on one side. So subtract 48r minus 9 equals 0. Okay. We wrote our original distance equations, set our times equal to 1/4, solve the rational thingy, and now I'm left with a quadratic. How many solutions will we get with a quadratic? Always 2. That's right. Usually 2, definitely 2. So one of them, in this case, one of them will make sense, one of them will not every single time. We're solving for a rate. You're going to get a negative answer and a positive answer. Obviously, only the positive one is the one that makes sense in this situation. All right, factor or quadratic formula. Nothing's going to factor to well, no two integers will factor to -9 and add to -48. Those aren't going to be integers. They're going to be randoms. Okay, so R equals opposite B, positive 48, plus or minus the square root of, actually, I don't even usually write the square root. I just use my calculator here. The square root of B squared, so negative 48 squared minus 4 times A times C, which is -9. So I do all of this right on my calculator just to save me. Like, I don't even do that. I find out what's on the inside of the square root. That's not right. Why isn't that right? That should be a positive number. Because, I know why. It's negative 48 squared minus 4 times -9. So it's 2340, and then the square root of that is 48 point, we'll just do 48.4. Now, all over 2a, which is 2. So this is me applying the quadratic formula. Right away, you should be able to tell me there's one answer, one correct answer. Is it going to be the answer when I add or subtract these two numbers? Adding, because when I subtract 48.4 from 48, then you're going to get a solution that's negative, and it's not going to make sense. So we're solving using addition. So that plus 48, then divided by 2, and we end up with 48.1 miles an hour. Okay. So that's a long process. We're going to do a different type of example and then revisit that process again. So the other type of problem, now this is a problem unique to the strategy of solving rational functions. So these types of problems where you're given the total time and you're asked for rate relative to still water or like without a tail or headwind, because some of these are airplane problems. That's the process you're using. The next type of problem that you're going to use your ability to solve rational functions is work problems. And if you've taken a physics class, you've probably done work problems where different portions of a task are done at different rates, and then you find their combined rate. So if it takes Devin 10 hours to clean an attic, Cody can clean the same attic in 7 hours. How long would it take them if they work together? Obviously, it's not going to be between those two numbers. Like if you've got someone who can clean it in 10 and someone who can clean it in 7, it's going to be shorter than 7 if they're working together. So it's not like you're just averaging numbers. So here's my approach to these problems. So if it takes Devin 10 hours, what's his rate? What portion of the attic does he clean per hour? Did you say 1/10? So his rate of cleaning is 1/10 of the job is completed per hour. Cody can do the same job in 7 hours. What portion of the job does he complete per hour? 1/7. We are asked to find out the time it would take if they worked together. So let's say it's T hours. Their combined rate, follow the pattern. What's their combined rate going to be? If it was 10 hours, 1/10 per hour. 7 hours, 1/7 per hour. T hours together, 1/T, the portion 1/T per hour. So first take all of your times, think of them in terms of rates, and now we know that this rate plus this rate is going to equal this rate. So the rate of 1/10 per hour plus the rate of 1/7 per hour is going to equal the rate of 1/10 per hour. Now we just have a simple rational equation to solve. So I want to eliminate all fractions at once. So what am I going to multiply by? By what? Common denominator. So 10 times 7 times t in this case. So 70t. 70t. Okay, so when I multiply 70t by 1/10, the 70 and the 10, and you could even write it like this if it helps. Like don't skip too many steps if you get lost. So I won't skip these steps. 70t over 7 plus 70t over t. So I've multiplied everything by 70t, and now I'm going to simplify. 70 over 10, 7t, 70 over 7, 10t. And then on the right-hand side, the t's cancel. So 17t equals 70, and then divide 70 by 17. You get about 4.1 hours when they work together. It should always be lower than both of them. So we're not averaging the times, we're finding the combined rate. So in these problems, we don't have time for another one of these, but they are all the same way. Yeah. Exactly. Yeah. So these, when you multiply by the common denominator, it's always going to result in those two things. Yes. So that's going to happen every time. I would encourage you to break it down, write their times, convert their times to rates per hour, and then add the rates, but then that will always happen if it's set up correctly. So I'm not going to do more of these just because I want to work through a different kind, but it's always going to work like that. Okay, I want to at least start. Let's see. Yeah, last page 26. I want to start problem 15. Okay, the air distance from Chicago to LA is about 1,800 miles. According to the airline schedules, planes are expected to be in the air for about 7.5 hours. So that's the whole combined trip. If the typical tailwind from LA to Chicago is 45 miles an hour, what is the expected speed of the airplane in still air. So this is a cool problem because pilots do anticipate tailwind or headwind, and it does change their time because they're either fighting against it, slowing the plane down, or sometimes if you take enough flights, eventually your pilot, you'll probably hear one time say, hey, we've got a tailwind, we're going to arrive 15 minutes earlier than we expected. And those are always great announcements. So, all right, so we've got 2 trips. Now, honestly, it doesn't matter if you're like, wait a second, does a tailwind mean it's pushing it or stopping it? It doesn't matter because it's either going to be R plus 45 or R minus 45. And in the end, it doesn't matter where they go. So let's say it's 1,800 miles. The round trip is 7.5 hours. So distance is 1,800 from just one way. Let's say on the first trip, they're facing the wind. So that would be a headwind coming at them. So their rate would be whatever speed they're set to minus 45. And then the way back, it's the same distance, same route, but assuming the wind direction didn't change, it's going to be working in their favor. So it would be R plus 5, and that's obviously going to be or 45, a different time because it is going to cut their speed down a little bit. I'm going to shut this door really fast because they might start tapping. Okay. All right. So now what? What did we do last time? We still haven't used the fact that the total time is 7.5 hours. Huh? 7.5. Okay. So let's keep that in mind and solve for T1 and T2. So T1 is 1,800 over R minus 45. I can solve for T2 here by dividing by R plus 45. And I know they add up to 7.5. So I prefer not to deal with decimals and fractions in the same problem. So I actually rewrote 7.5 as 15 over 2. So just because I know that when I double 7.5, I get 15. So then you can rewrite it as 15 halves. So I like that better just because then I don't deal with fractions and decimals. And then you're not doing the quadratic formula with fractions. So you would set up your final equation. 1,800 over R minus 45 plus 1,800 over R plus 45 equals 15 halves. Okay, so all of that work just gets us to the setup of this rational equation to solve now. So now we want to get rid of every fraction. So I'm going to find the common denominator. Jordan, what's the common denominator going to be?
2 times R minus 45 times R plus 45.
Good. 2 times R minus 45 times R plus 45. So all of those 3 combined. Plus 45, R minus 45. Okay. Now, carefully multiply by everything on the left. When you multiply by the first fraction, whatever the denominator is, it's going to cancel with that piece of what we're multiplying by. It's going to leave me with 1,800 times 2, which is 3,600, R plus 45. Just a warning, you're going to be working with big numbers. That's okay. Big numbers work just like little numbers do. Multiply by the second one. The R plus 45 denominator will cancel with the R plus 45 numerator, and you're left with 1,800 times 2, which is 3,600, times R minus 45. On the right, the 2's cancel, and you're left with 15 times R minus 45 times R plus 45. Okay, so the fractions are gone, but we've just got some big numbers to work with. So we're going to distribute the 3,600. Don't get nervous about these large numbers. So 162 is 3,600 times 45, 162,000. Wait. Plus another 3,600 minus 162,000. So that number is going to go away every time when we do this type of problem. So these two cancel each other out. And then you'll have 15 times this r squared plus 45r minus 45r, and then the square of 45, which is 2025. Okay, I'm gonna write one more step and then I'll leave it. So 3,600r plus 3,600r is 7,200r equals 15r squared and 15 times 2025. 30,375. Okay, these big numbers typically bother people. You have the option, now that we can see it's a quadratic, you're gonna get it all on one side and you apply the quadratic formula again. When you do, so these problems are pretty meaty, and you just need to make sure you're staying organized with all of your values. But you could, if you wanted smaller numbers, factor a 5 out, and then you're just dealing with smaller values, but in the end, you should always end up with that same value. So we'll stop there. You've seen 2 examples of this type of word problems, and then again, the one with the work. But that's it for you guys. So you guys, I want you to come in on Tuesday with that worksheet done. Let me stop recording.